Here's the thing that's been driving quantum researchers crazy for decades: noise. Imagine trying to balance a pencil on its tip while someone's shaking the table. That's what quantum computers have been dealing with. They're incredibly powerful, but so sensitive that even the tiniest vibration destroys their calculations. But scientists from MIT, the Niels Bohr Institute, and other top institutions just cracked the code. They've created something called frequency binary search. And it's basically like giving quantum computers superhuman reflexes to fix their own problems in real time. Let me explain why this is absolutely mind-blowing. Quantum computers work with qubits. Think of them as the most sensitive measuring devices ever created. They're so precise they can detect changes smaller than an atom, but that's also their weakness. Any tiny electrical or magnetic shift in their environment scrambles their calculation. Until now, fixing this noise was like trying to hit a moving target while blindfolded. By the time scientists measured the noise and tried to correct it, the noise had already changed. They were always one step behind, playing an impossible game of catch-up. This new algorithm changes everything. Instead of taking thousands of measurements to calibrate each qubit, which is painfully slow, it can calibrate all qubits simultaneously with exponential precision in less than 10 measurements. We're talking about going from hours to seconds. Dr. Fabrizio Berrita, who led this research, put it perfectly. You can measure the actual noise, and once we know the noise, we can correct the control path to mitigate the decoherence. But here's the kicker. They're doing this in real time, while the quantum computer is actually working. Think about what this means. We've been stuck with quantum computers that have dozens or maybe hundreds of qubits. But this breakthrough could unleash systems with millions of qubits. We're talking about computational power that could simulate entire molecules, crack encryption in minutes, or solve climate modeling problems that would take traditional computers thousands of years. And this isn't theoretical anymore. They've already tested it using real quantum hardware with field programmable gate arrays that can control qubits directly without the delays that killed previous attempts at noise correction. The implications are staggering. Drug discovery could be revolutionized. Imagine simulating every possible molecular interaction to design perfect medicines. Financial markets could be predicted with unprecedented accuracy. Weather forecasting could become so precise, we'd know exactly where every raindrop will fall.